Hello. Okay. Hopefully I get some. Okay, right. Screen. Hello. Hello, and welcome to Doc Clay's chemistry lessons. Hopefully you can hear me. Hopefully you might be able to see my screen now. Really big apologies for all the issues that we've had so far this evening. It's been one of those tedious technical nights. So perhaps first of all, people could just give me a shout if they can hear me and if you can see the broadcast. Thank you, Anon 1624, smashing. I'm live. I'll just let everyone know in the room. We are live now. Evening, Holly. Nice to see you. Hello, Joe. Good to have you on board. Yep. As I say, sorry about that. It's been one of those evenings where everything that could have gone wrong has gone wrong. The chat had disappeared for you. It's back. When you say the chat, Joe, do you mean this rather horrible green one or the black one? Hello, David. Both were missing. Okay. Yeah, the chat which I had updated, spent some time yesterday doing, seemed to have disappeared. I'll make sure that's up and running, and we'll go with this chat tango for this time, and hopefully we'll have the new chat up and running for the next session. Yes, it's a horrible green one. Like I say, that should be up and running for next time, and we shall see if we can get the chat it's called, as a plug-in to work properly for us next week. Right, okay. Hopefully you've had a good couple of days. And you've had the chance to digest some of the work that we went through last time. Just to show you where we were up to, we had a look at all of the mechanisms here from the AS and the A2 course, and we also looked at synthetic routes, and we were having a play around with some multiple choice questions towards the end of the session, and there were heaps more in that book to keep you going. I thought what we'd do this evening is really just look at some of the year one questions, overview and spectroscopy, and then we might go and have a look at some of the year two, 1 and 2, sort of more in-depth questions. So we'll see how we get on as we progress through the evening. We'll have a look here at some of these year one overview questions to start off with, and this is actually a really nice sheet that we use here to look at infrared spectroscopy. Now, it's probably been a while since you do it, so one of the other questions I want you to think about this session is whether you want to do some work on proton NMR spectroscopy next week. So just while I'm setting this up, if any chatters think that they would like to see some proton NMR next week, do just put that in the chat, please. Okay, so I thought you might want a bit of infrared. Definitely, will you be covering a video? Joe, there is a really good video on it in the sessions by eRentool, but whether I get a chance to actually write a NMR video, I don't know, but we will certainly do plenty of stuff in the session, in the webinar session next week, and we'll do lots of questions. Yes, and I'll certainly do carbon NMR too. It's much easier, thankfully, than proton NMR anyway, the carbon NMR, but we will certainly look at that. Okay, so the spectroscopy that we'll look at today is from the AS course, which is just the infrared spectroscopy. And the key thing about your infrared spectroscopy, the questions we'll look at the moment, is it identifies functional groups. Cool. I'll bring up the NMR. So infrared looks at functional groups, and when you're looking at infrared spectroscopy, your key thing is you need to be able to look at this data sheet. So here we have important information, and the infrared absorption data you'll find on the left-hand side. Table B and C are for NMR data. Like I say, we'll see next time. As we look at this, the infrared then is simply a measure of absorbance or transmission. It doesn't really matter which one you use. And we have a scale along the bottom here, and that is in wave numbers. And like I say, we'll see some examples in just a minute. And that's centimeters to the -1, and this is usually on a scale of 0 to 100%. Infrared simply works by having a light source, and that's an infrared source, and you shine it through a sample, and then on the other side, a bit like the calorimetry that we saw the other day, you have a detector, and you measure anything that doesn't get absorbed by the sample at the detector. And what you tend to end up with is some sort of spectrum that's sort of got jagged lines like this, and then maybe some more there, and then you get down to this sort of region at the bottom. Okay, the key things are there's a cutoff here about 1500 centimeters to the -1. Below that, we call it the fingerprint region. And this is good for comparing with known data samples when you're down on this region, and everything between 1500 to about 4000 centimeters to the -1, this region has specific absorptions due to the vibrating of functional groups. Okay, so that's what we get. The absorptions occur at these particular regions. So on our data sheet, to be quite honest with you, I never really understand why they are. These two at the bottom are in the fingerprint region, and you can generally ignore them. The nitrile group is sometimes used. The rest of the absorptions are really important. The key ones to note are we get this for OH, you get a broad peak at about 3000. About 3,200, while the OH acid, so this is for an OH alcohol, the OH acid always looks like this, and it's got sort of this funny little peak bit at the bottom, and this is downshifted more like at about 2,500 to 3,000. The reason it's got this sort of funny sharp bit underneath is because it always has carbon hydrogen stretches overlaying it. So what you have for the acid stretches, you sort of got the broad OH peak, and then you've also got these sharp carbon hydrogens which overlay it. And then when you sort of overlay the two, we have something that looks a bit like that. All right. We're going to use this data to recap all of our year one mechanisms and synthetic routes from last time. And we'll look, and it will also help us review the infrared spectrum. So here we go. Hopefully you've all managed to download the sheet here that says Organic Review Year 1, Overview Questions and Spectroscopy. Okay, if you've not already had a go at this, let's do so together. This is really, it's not so much a past paper question, but we're using it because it covers so much of the chemistry. So the questions you'll get in an exam are generally slightly more structured than this, and you get more opportunities to answer them. All right. Has everyone got a copy of this Organic Year 1 and the spectroscopy sheet, either on screen or as a piece of paper? Okay. No one shouted no so far, so we'll carry on. Great. It's good to see the chat still working. Thanks, Anon1624. Okay, compound D then, which is branch chain haloalkane, it says, was found to have a composition by mass of 39.8 carbon. So here is, and this would be a classic way they might ask you about empirical formulas actually. If you can't remember empirical formulas, you'll get a bit of a refresh here. So 39.8 carbon, 7.3 hydrogen, and the rest we're told is 52.9 is bromine. We're told that there are two peaks in the mass spectroscopy or spectrum, and the molecular ion peaks at 150 and 152. Any ideas why there's two peaks? So, okay. So the reason we actually get two peaks here in as a molecular ion, so if we're not aware of this, we'd get multiple peaks. This is from our mass spectrum. You need to know about time of flight from your year one course. It's because there's going to be two isotopes here of bromine. So we actually have bromine 79 and bromine 81. So that's why we get multiple molecular ion peaks. Yeah, well done, Joe. And they're of approximately equally intensity because they're about 50 minutes, slightly heavier on the 79 side. And then we're told some information. So it says E reacts with sodium bromide to form F, whose infrared spectrum is shown. So F does not undergo dehydration with concentrated sulfuric acid. F reacts further with acidified potassium dichromate to form G, whose infrared is also shown. So let's quickly do the empirical formula to work out what is what. So I just realized I've not even got a calculator in front of me, so perhaps some of you could do the maths for me. 39.8 over 12, 7.3 over 1, and 52.9 over 80 gives us certainly 7.3. See if I can find the calculator here. Smashing. 3.3, 7.3, and the final one is 0.66. We divide here by the smallest, so we divide through all by 0.66, which gives us one hydrogen, sorry, one Br. Is that 4 carbons? Five, 11, 1. Smashing. 5, 11 to 1. So what we end up with is a molecular formula here for our substance, which is C5H11Br. And so the first reaction then, this is what we got for E, is reacting with sodium hydroxide to form F. From our reactions the other day, we should be able to work out what sort of reaction that is and what sort of product we would expect to form. There's 2 pieces of evidence for that. Who fancies identifying what F is? Good. Okay. So 2 options. You're absolutely right. It could be, as we saw, if we come back to our synthetic roots that we saw the other day, we've got a haloalkane here, and we could potentially have an elimination, like Anon said, at 1624. But if it was going to be an elimination reaction, we'd form an alkene. The other option is we could form an alcohol. So both of those are possibilities. Joe suggested it's an alcohol. If we have a look at the actual question, its infrared spectrum is shown in F. Here, in our infrared, we have this broad peak at around about 3,200 centimeters to the -1. This indicates that an OH is present, and therefore we've not formed the alkene, so it's not an elimination reaction, but we have indeed formed a alcohol group. And if we formed an alcohol group, the reaction must be the nucleophilic substitution reaction. Okay, so from F, it then says whose infrared F does not undergo dehydration with concentrated sulfuric acid. We'll come back to that in just a moment. F reacts further with acidified potassium dichromate to form G. What functional group do we see present here in G? If we've got a broad peak that looks like this, and a sharp peak here, what functional group are we observing here? Well done, Anon. So we've now got an OH in an acid. So we've got a carboxylic acid. So F is going through to form C5, H11, C. Oh, sorry, C. Hey, well, there we go. So between David, Joe, and Anon, I think we've got carboxylic acid is indeed what we've got. We've got somewhere here, we've got a C double bond OH, and then we've got the rest of the molecule, which we know is C4 H. It's going to be C4H9. Okay, so that's what the rest of the molecule is. How do we get there? How do we get there? Indeed. F reacts further with acidified potassium reactor to form G, whose infrared spectrum is also shown. Draw the structures and name E, F, and G. Identify the species responsible for the peaks at 150 and 152 in the mass spectrum. Okay, so what we found out is G will go forward and be oxidized completely to the carboxylic acid using potassium dichromate. Anyone know the color change we'd observe here of the potassium dichromate as we go from the alcohol to the carboxylic acid? David, definitely spot on there. Orange to green is the correct one. So we observe orange to green. Also, other bits of information that we're now starting to get. Fantastic. Well done, Holly. We're also told that this F does not undergo an elimination reaction to form an alkene. So this reaction does not occur. Other bits of information. F going to form the carboxylic acid. What sort of alcohol must F be? Absolute, yes. So it's got to be a primary alcohol. Well done. So F, you're absolutely right. It needs to be a primary alcohol. So a primary alcohol then looks like this. So that's the first piece of information. The second piece of information is if it does not go under elimination reaction, what does that mean about our primary alcohol and the carbon next to it? That's the exact question. So why does it not undergo dehydration or elimination reaction? What does that mean about the adjacent carbon? Okay, Holly. So it has to be primary because, so it's a good question. Primary alcohols will oxidize to aldehydes and then further oxidize again to carboxylic acids. Secondary alcohols, though, will only oxidize to ketones, and there's no further oxidation, and tertiary alcohols do not get oxidized at all. Joe, that's so Holly, there we got the reason why it's primary. Why does it not undergo dehydration? That's absolutely right. It's for dehydration to occur, and I'll jump back in a second to the mechanism sheet to show you. This carbon, which is adjacent to the alcohol carbon, has no hydrogens on it. So that means each of those carbons must be, sorry, each of those positions must contain a carbon. And if we actually count up the rest of the hydrogens, we'll find out that each of these are methyl groups. Just to show you why this is the case, I'll come back to our mechanism sheet and we'll look at our elimination from this is the elimination that we're talking about. So for the elimination to occur from acid catalyzed from alcohol, which is the one that we're looking at, we require on our requires a hydrogen on the adjacent carbon to the OH group. And what that therefore means is if we come back to our question here, none of these can be hydrogens because we're not observing the elimination reaction. Okay. Are we happy with that idea? Great. Okay. What we therefore know is that our G, well, we already knew part of what G was. G must be this. Great. So as we're going through, if you update your sheets from the other day as well, there we go, H3C. There we've got our carboxylic acid, and our E must also be then carbon, 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 Br to start with. So there is a lot of chemistry actually from our year 1 course, along with starting to implement some of our infrared spectroscopy. Oops, made a mistake. These of course should be methyl groups. Okay, no questions so far? Well, that's jolly nice to hear from you, Cortana. I'd have been quite happy if you just didn't run 300 updates before I was running a live webinar, to be quite honest with you. All right. So let's have a look at question 2, and then we'll start looking at some of these past exam questions on the year 1 and the year 2 course. Any questions so far? No, great. Okay, brilliant. So question 2 then is now looking at propene, and I'm just going to actually create a new page here so that we can look at this slightly better on a new page. So just bear with me for 1 second, please. There we go. Okay, so we got a nice fresh page now to look at this question 2 without the disturbance for all those bits from question 1. Okay, so propene now. So propene here is an alkene. If I come back to my organic mechanism sheet, sorry, my synthetic root sheet that we've got here, we can see our alkenes are likely to do always addition reactions. So we're looking for some sort of addition reaction with an electrophile. Here we've got a propene reacts with HBr. Just while I'm going through this, what is the issue that we've got to consider as we're talking about all of this of propene? Now I'm going to draw this as a skeletal formula. Make sure you're happy with skeletal formulas. So here is propene. What is the issue with propene and HBr? Two products, absolutely, Joe. So here we're going to observe the potential for two products. Why are we going to see two products? And which product are we most likely to see? One or two bromopropane, absolutely. And which one is going to be the major product and which is the minor product? So we're going to end up with two products. We're going to have BR and potentially BR here. Yes, Anon, you're absolutely right. 2-bromopropane would be the major one. If we just look at the reaction mechanism, remember we saw these yesterday. We have electron density to the delta positive carbon from the bond onto the bromide, and what we end up with is we end up with two potential carbocations. We either have one on the second position or on the position 1. This one is more stable and this is less stable, and therefore what we end up having is the Br minus that we've got left over here will preferentially attack, or is more likely to attack here. So we end up with a major product here because the secondary carbocation is more stable than the primary carbocation. I should just circle those to show it's carbocations. Okay, so we know we're going to have propene to form H. We know that this is going to be H. H reacts with sodium hydroxide to form I. So this is going to react with NaOH. What sort of reactions could occur with sodium hydroxide? Okay, it's a fair question there, Joe. Do you assume it's the major product? Yeah, always look at the rest of the information just to check that there's no other pertinent questions that you need to be aware of. Generally speaking, they're probably going to be talking about the major product. Often, if it's talking about major minor products, one of the key things is that they will start asking about your major minor products. And on spot on, it's either going to be elimination or a nucleophilic substitution. In this case, we can see that warm acidified, reacts with sodium hydroxide to form I, and I reacts with warm acidified potassium dichromate. So whatever happens here, we're going to react with H plus and K2Cr2O7. It's going to be orange to green. What sort of things react with acidified potassium dichromate? And therefore, what sort of reaction must be happening here with our sodium hydroxide? Absolutely, so it should form an alcohol. There we go. Question is, what sort of alcohol is this? And therefore, what sort of product are we going to form with the reaction of acidified potassium dichromate? Absolutely, this is indeed nucleophilic substitution reaction. And what product are we going to form here? Absolutely, so we end up reacting to form the ketone. And Etoan, you're right that this is indeed a secondary alcohol. So here we'd observe the oxidation of orange to green to form the ketone. It doesn't go and form the acidified potassium dichromate. Finally then, let's have a quick look at our infrared spectrums. Let's see if we can identify, here we've got H, here we've got I, and here we've got J. Which spectrum relates to which of our substances, H, I, and J, and we simply look for 3 key features, or 1 key feature in each one. So starting with J, what is the functional group that we need to identify? And therefore, which infrared spectrum is it? Spot on. And on C double bond O, we were absolutely right. The C double bond O is around about, well, if we ping out our data sheet, we can see it here, 1680 to 1750. If we look carefully, well, this one certainly isn't it. And if I look at spectrum 3, well, there's nothing around about 1600. So indeed, this is our ketone. I then? Which one is I? Absolutely, and it's I because we've got this broad OH stretch around about 3000, which leaves us the final one here, which has to be H. Okay, smashing. So in terms of the nucleophilic substitutions, well, that we've seen, we haven't looked at the nitriles, but we'll see some in a minute in our year 1 and 2, but it has dealt very nicely by looking at our nucleophilic substitutions to form alcohols, as well as elimination reactions from our year 1 chemistry, and started to recall some of our infrared spectroscopy. We're now going to go, I'm just going to pause because I think I'm going to sneeze. Hang on. Hopefully my microphone mute worked there and you didn't hear me sneeze all over the place. If you did, I'm terribly sorry. Cheers, all. Etienne, how would you advise we approach questions at most proton NMR and carbon NMR to identify the structure of a compound? Good question. We'll be looking at spectroscopy, particular NMR and carbon NMR next week. Really, with all of these sort of structural and spectroscopic techniques, it's really a case of taking each piece of evidence one at a time and trying to find out what piece of information you can glean from that, and then from there sort of just writing everything down and then building your puzzle up one piece at a time. And like I say, we'll practice spectroscopy and that sort of thing in the sessions next week. I also plan to look at amino acids with you next week because I know that's a new part of the course, and I think potentially sort of one of those areas that staff aren't necessarily the happiest at looking at. Cool. All right, so we're going to move now to look at some of these questions here on organic synthesis, year 1 and year 2. So this is covering all of them. They're past paper questions. And as we go through, I'll identify any ones which we haven't really done. And on 2838, when you say yes please, is that yes please to amino acids or yes please to spectroscopy? Okay, cool. All right, so let's start having then a look at some of our past paper questions. Hopefully you've got these either on screen in front of you or printed out. You may have even had a go at doing some of these. We're going to spend best part of sort of 45 minutes, half an hour, 45 minutes. Let's really try and work through as many of these as possible. So as we're going, don't be afraid to put your answers in the web chat. It'd be great to see them. Don't be afraid of getting it right or wrong, really doesn't matter. Or asking questions of anything that you're not sure on. Remember, the whole point of this is that you're improving it and helping you to work through the exams. So the N-substituted amide C6H13NO can be formed from butene in a 3-step synthesis. So the key bits of this question really is it's an AS, so it's synoptic in that sense, and it's covering everything that we saw last time. Now it points out here detailed mechanisms are not required. That is quite possible. They might say that for your AS course, but there's no reason why they can ask you for mechanisms as well. So we'll identify what the mechanisms are. So we've got 3 reactions, we've got 9 marks, and we've got to do 3 things for each question. So when you're answering these, I would encourage you to simply write out reaction 1, reaction 2. Don't get bogged down with writing heaps and heaps of sentences, because no one gives too much bother for that. Simply reaction 1, reaction 2, reaction 3, and then write down the conditions. So let's go for it. Reaction 1. Anyone fancy a go at reaction 1 there? Ah, the chat stopped again. HBr, fantastic. So we've got HBr. We're picking up 1 mark. The name of the mechanism. Now let's just check here. The name of the mechanism. Yeah, I think just be careful there where you're giving your name of your mechanism. Make sure you're explicit, not just addition. Yeah, so anon 3085 and 3158, electrophilic addition is really what we're looking at for the mark. Philic addition is the name of the reaction. The structure of the product is indeed 2-bromobutane. Yeah, we can't get 3-bromobutane, remember, because that's going to be the same all around. So indeed, 2-bromobutane is correct. Okay, what about reaction 2 then? Reaction 2 here, we're using, well, you're going to tell me what we're using. Okay, now I'm really pleased that we've asked this. Few possibilities now. Just with, first of all, let's look at the reagent. Certainly in all cases, nucleophilic substitution is absolutely spot on. So nucleophilic substitution, well done. That is spot on. If we look, C4H9Br is where we're at, and we're wanting to form C4H11N. Now, not addition. Yep. Okay. So take a step back here. This is indeed the nucleophilic substitution that we're looking at. If we go back here to our synthetic roots, remember here that if we're using KCN, if we're doing nucleophilic substitution with a nitrile group, then the key here is that if we're adding KCN, then we add one carbon to the chain. And in that instance, if we come back and have a look at our reaction here, we're not adding any more carbons to our chain. So this is not the addition of KCN. Yep. So yeah, well spotted there, 3158. This is indeed a reaction using NH3. If you count up the carbons as well, and the hydrogens and the nitrogens, they're just giving you the molecular formula here to sort of try and confuse you a little bit. That actually works out that you got C4H9NH2, which would have made it a bit more obvious, I think. And absolutely, Joe. So the key thing for identifying whether or not you're using KCN versus ammonia is going to be that carbon chain length. So the question there, whether you're going to use so lots of you are writing they're concentrated. We don't need to worry about concentrated. Simply an excess of ammonia is all that's required. Okay, and in fact, they're only really interested in the reagent. Absolutely, if they're asked for a condition there, you would require an excess of ammonia. The name of the product then is actually 2-aminobutane. Sorry, I didn't see if anyone got that correct when we were going through that. Okay, and then the final step, reaction 3. Hopefully I've just answered that, 3158. Yes, 3158. I will certainly do naming compounds. Also, I've got quite a lot of videos. Hold on at the end, I'll direct you to good video content there I've got, and I'll send you some appropriate worksheets for practicing naming compounds. It's certainly something you've got to be able to do. Let's have a look then at reaction 3. What do we think? First of all, what's the functional group that we're forming in? Anon 3158, spot on, well done. It is indeed a nucleophilic addition elimination reaction. We are indeed adding 2 carbons to our chain, so it is indeed using CH3COCl, which is ethanoyl chloride. Joe, I'm afraid it's not a secondary amine here. It is a reaction between the aminobutane and a ethanoyl chloride. It is an amide, well spotted. It's actually a secondary amide. Let's see who's going to give us the answer here. Oh, that's true. In fact, we don't. I've just realised. Sorry, of course, the question is asking for draw. It's actually not asking for the name here, but the structure, and the structure here forms by. I'll just do it over to the side here, where we have C double bond O CH3. Question is, how do you name that? If you wanted to name it, it would be N-butyl ethan amide. Okay, so they're culminating using both AS and A2 knowledge. Okay, what I want you to have a go at then is compounds Z can be formed via compounds X and Y. All right, so question 2, have a quick go at question 2. I'm just going to go and get a power supply for my computer. I'm going to give you a couple of minutes there to have a look at question 2, and I will be right back. Hello. Sorry about that. I've got power again, so we should be able to keep. Hello, hopefully you can still hear me and see me. Okay, I just lost internet connection, so I'll be back. Great, okay. Sorry, just dropped out for a moment then. So let's have a look then. Indeed, okay, so well spotted. Compound X here. Identify compounds X and Y and give reagents and conditions for step 1 and 2. So let's start there. So here we are, step 1. We are increasing the chain length. So indeed, KCN, spot on. Dissolved in ethanol to form ethane nitrile. Yes, well done. When you're doing your naming there, the question is whether you do you put in the E or not? And the rule here is that nitrile, if you add the E if two consonants together. Okay, so if it's a vowel, then you don't need the E. Okay, so KCN dissolved in ethanol to form ethane nitrile. Yes, so in ethanol, and you're forming ethane nitrile. Smashing. Then step 2, C2H7N. So what does it look like that we've done here? So actually, let's just okay, so question 2, or step 2, if you're not aware of this, just make sure you are. It's one of the synthetic routes that's often missed, and people aren't aware of it. Doesn't matter which one you choose, but you're basically doing the reduction of a nitrile, so you're adding hydrogen, and you can do it with lithium aluminium hydride with a dry ether, or you can do it with hydrogen with a nickel or platinum catalyst. So yes, you're absolutely right there. Anon, it is a reduction, nickel hydrogen, spot on. So there we are, nickel, hydrogen, and it's a reduction reaction. The name of the product as we go, well, you could either have that as ethylamine, or you can have it as 1-amino ethane. Either way is acceptable. State the type of compound of which Z is an example. Anon, basically, just whenever if you're adding hydrogen, just as a rule of thumb, add hydrogen is equivalent to reduction. Okay, as is add oxygen is equivalent to oxidation. Yes, so it is indeed a secondary amine. Well done, Joe. 3158. I don't quite understand what the hat is. Compound Z reacts with a large excess of bromoethane to form a solid product. Draw the structure of this product and name the type of mechanism for this reaction. Okay, so what is the solid product going to be if we're reacting it with bromoethane? And what are they trying to get us to work out here? Holly, that is when you have got nitrobenzene and you're going to make a phenylamine. So just to explain there, Holly, there's a reduction. Absolutely. You're well done, those who realise we're forming a quaternary ammonium salt. Anon, okay. Anon 315. Let me. Yes, you simply add the square brackets 315, and it's essentially it's normally an addition of hydrogen, so there's only one product. You simply add enough hydrogens to that you need in square brackets. It's anyone work out what the name of the quaternary ammonium salt is? I'm going to draw it. Oh no, sorry. Ask for the. What's the name of the mechanism? So it's with bromoethane. So we get C2H3, C2H3. This is for the we need it in square brackets, and strictly speaking, although it's not required, we get a bromide. Yes, Joe, well done. I read that as bromoethane. You're absolutely right. Nucleophilic substitution. Joe, you're very close. Trimethyl, ethyl, ammonium bromide is actually how we name it. I was wrong. It's not C2H5. It's bromomethane. I missed the M out. Thanks. No worries. Cool. Okay. Sorry, that's me messing with the maths. Let's have a look. Let's carry on. Let's see where we're up to. Okay. So tests, make sure you're happy with your tests. Describe how propanol. The question about part 2 here we'll deal with next week. Chemical tests though, aldehydes. Make sure you know the test for the aldehydes. Here, the aldehyde ketone test. There's 2 of them. Absolutely. And so we have 2 possibilities, tollens and failings. Positive test, please, for tollens. Absolutely. So silver mirror now in, and this is also something you need from your transition, silver mirror in aldehyde. And that's because you had the Ag plus being reduced to form silver. And the failings in D goes from blue to brick red precipitate. And you're actually getting a change there in oxidation state of the copper 2 plus to the copper 1 plus, and hence why you get a color change, because you've got a change in oxidation state of the copper ions. Brilliant. Okay, so compound Z can be produced by the reaction of compound X with compound Y, as shown in the synthesis outline below. So here we've got an aldehyde. Here we've got a ketone. Identify compounds X and Y for each of the 3 steps in the synthesis, name the reaction involved. So somehow or another, we've got to go to X and Y, and then we've got to do this reaction here to form Z. This is requires quite a bit of knowledge, actually. It requires you to know what 2 molecules you can form this from. So the question is, what 2 sorts of molecules can we form this from? What's WOW 4361? Absolutely, well done, because this is a esterification reaction, and it's going to be formed from an alcohol. They react to form an ester. Brilliant. So we're forming carboxylic acid and an ester. So CH3, CH2, C double bond OH, and the other one is going to be an alcohol. Obliterated it 4361. That's fantastic. So X is indeed going to form CH3, CH2 carboxylic acid. So that's propanoic acid. And here we're going to form the alcohol. So to get to step 2, how do we do those reactions, of course, is the next question. So we want to form the alcohol from the ketone. How do we go from the alcohol to the ketone? Sorry, from the ketone to the aldehyde. I'll start again. From the ketone to the alcohol. What? Okay, so yes, Joe, indeed, the aldehyde, the propanol, will indeed be oxidized here by, so that is an oxidation. Step 2 is a reduction. Well done. Yep, fantastic. So this we are H plus K2Cr2O7 and reflux for the oxidation. And well done. This is sodium borohydride. Any ideas what's the name of the mechanism here for the secondary alcohol, other than a reduction? It is anon. Well done. It's a nucleophilic addition reaction with the reaction of hydride ions. Fantastic. Okay, here we go then. So this question here, question 4, we can already see something important. We see the benzene ring. As soon as we see the benzene ring, what sort of reaction mechanisms are we thinking about? Yes, the name of the mechanism. So acylation, what's the name of the mechanism when we're looking at things like benzene? Okay, careful here. We're not electrophilic addition. So benzene is not an addition reaction, and that's because the benzene is more stable than an alkene, or than the trialkene that it could form. So it's not electrophilic addition with benzene, but addition elimination. No, so that's right. It's an electrophilic substitution. So whenever you see benzene, you want to be thinking about electrophilic substitution reactions. The synthetic routes here are on the second page. So these are the ones. Here's our electrophilic substitutions. So be aware of those. In reaction 1, ethanol chloride and aluminium chloride are used to form a reactive species which then reacts with benzene. Write an equation to show the formation of the reactive species. So here, you're given lots of information here. You've just got to be able to see if you can actually use it. I'm going to run out of space. There we form aluminium. It's getting late because you can see I'm aluminium tetrachloride. And the carbocation. Name and outline the mechanism by which this reactive species reacts with benzene. Okay, so I'm not going to draw. Okay, I will do actually. Make sure just to highlight the point, we looked at the mechanism reactions last time. When you're drawing these, if you've had a go, you've got the positive. Now remember that could be NO2 or the acyl group there, through the carbon onto the delta positive carbon. Your intermediate, make sure, that's a little bit exaggerated there, that your positive charge is pointing towards the carbon there that it's joined, and that the hydrogen is hanging off. Make sure when you're drawing these as well that your curls or your half circle doesn't go past position 5 or 6, and then the hydrogen comes back in the second step for your mechanism. Make sure you draw your mechanisms are accurate, because you will lose marks if they're not accurate, and they're often worth quite a few marks. So drawing something like that, you'll get 1 mark for the first curly arrow. You normally get a mark for drawing the intermediate and a mark for the correct curly arrow. So you're looking at 3 or 4 marks there. 4b then, sodium borohydride, NaBH4, is a possible reagent for reaction 2. Name and outline the mechanism for the reaction with sodium borohydride in reaction 2 and name the product. Okay, so I'm going to do this one because it's quite useful for the fact about the product. So as I'm drawing this, check that you'll be happy with the nucleophilic addition. So this is now B with sodium borohydride as a lone pair of electrons. What I want you to do is not actually in the question, but to tell me about the product. What sort of isomerism will the product show and why? Oh, no, it's not. Oh, no, yes, it is. Sorry, because that's a... So tell me what sort of isomerism the product will show and why. So the first step there is the addition. Absolutely. So here we got a chiral carbon. It's got optical isomerism. It's got 4 different groups attached to it. Brilliant. Then the question is, why is a product optically inactive? So why is this product going to be optically inactive, even though, as you all correctly pointed out there, Oh, it's not a very good drawing. Apologies. It does indeed, Joe. So well done, Anon. We form a racemic mixture. Why? As it can okay, so be specific, Joe. As it can, so the hydride ion, so the H can attack, and the key here is that the C double bond O is planar either above or below the plane. Okay, so now, so what we end up with there is it will rotate the plane of polarized light equally in both directions, resulting in no change. Okay, so we sort of went through the mechanism there, but we also looked at some of the... Yeah, no worries. Is it really of... So the key about what we mean by something that's planar, Anon, is that it's two-dimensional. So when you... okay, let me deal with both these. Anon 3085, planar means it's two-dimensional. It's like a piece of paper. Okay? Whereas, and that's true for the carbon double bond O. Whereas something which is three-dimensional would be something which is tetrahedral, which would be something like the product here, which would be something we're used to seeing, like methane. So that is not planar. In other words, it's got three dimensions. Anon, so when you're asked to draw the optical isomer, do you draw the reflection or do you draw the hydrogen attacking from the other plane? 4361. If you're asked to draw the optical isomers, this is what you should do. I'll use the example above. Just so you're aware, this I'm going to redraw here on my picture as C6H5, just to basically to make my life a bit easier when writing it out here. We've got hydrogen, a methyl group, and an OH. If you're asked to draw two enantiomers, make sure that the easiest thing, I think, is to draw it almost exactly the same, but just simply swapping these two around. Okay, so those get swapped. That is the two optical isomers, and I find is the easiest way to draw them. I'm not sure if that answers your question, 4361. Okay, not at all 4361, but only swap two. Otherwise, you can get yourself in a bit of a pickle. Okay. We started a bit late, but it's 10:15 now. Yeah, that would have been fine, Anon. CH3 and OH would have been fine. Okay. I think we'll leave the polymerization reaction. We've not really looked at polymers yet, so we'll leave this one. what I plan to do, we started a bit late. I thought we'd go till about 10:30. Is that okay with everyone? As per usual, I will put the answers to all of this at the end of the session. Okay, what was the name of the product? Here I'd name this as a side group of a phenol. So this is, I would say this is 2-phenyl ethan 2-ol. And here I'm using the description phenol to describe the benzene ring as a side group. Apart from, of course, I should probably name that 1-phenyl ethan 1-ol. Okay, right. So I'll let you have a look at these in due course. Just be aware that you need to be thinking about intermolecular forces between these organic compounds. Remember, you've got 3 types: hydrogen bonding, dipole-dipole, and van der Waals. I'm not going to go through this question at the moment because it's really about polymerization. But do check through again. If you get questions, drop me an email, drop me a contact form, and I'll happily answer them, or can always pick them up in the sessions. Okay, so this question here. Here we go. This works quite nicely. I guess because we're now talking a bit about isomerism. And it also looks at a reaction here about racemic mixtures again. So P, Q, and R have the same molecular formula, which is C6H12. P can represent a pair of optical isomers, Q can represent a pair of geometrical isomers, and R can represent another pair of geometrical isomers different from Q. Okay, so geometric isomers, key thing here. Eight, 9, 10. Yes, happily. 8, 9, and 10. 8, 9, and 10. Yes, I tell you what, I'll jump to 8, 9, and 10 now, Anon. I think that sounds like a good idea. Have a look at question 6. We will jump to 8, 9, and 10. I'm really pleased also to hear that you did these, had a go at these before the session. All right. And that will probably take us up to about 10:30. We can always pick off the in-between ones if you like as we go through. So a possible synthesis of 1,4-diamine benzene is shown below. Identify a suitable reagent or combination of reagents for step 1. Okay, so step 1. With all of these, you really want to think about what you've got. So we've got here NH2, which is starting, but if we look at the product here, this is that's our product. Okay, so here we're forming an amide link. So although we've got a benzene ring, we've also got an amine, and because we've got an amine, we've got a lone pair of electrons, and therefore it could also be acting as a nucleophile. So this reaction is, in fact, and it's a good reaction mechanism because it's not one we've seen so far this evening, is, well, I'll let you put your hands up and shout out what sort of reaction mechanism you think it might be. And we've got two possible reagents we could use for this. Spot on and on, it is a addition elimination reaction. This is an amide link. It's formed between the nitrogen and either an acyl chloride, or it could be an acid anhydride. Well done. I'll go for the mechanism down here. So all of these reactions, nucleophilic addition reaction, the first reaction step you have is the lone pair of electrons attacking the delta positive carbon, going onto the oxygen. We form an intermediate, which has now got the H3C, the chlorine, and we've also got the NH2 coming off here. We've got the benzene ring, and there's a positive charge now on our carbon. Get 2 marks for the first step, for that correctly. Get a mark for drawing the intermediate correctly. Lone pair of electrons comes back in. You remove the chlorine, make sure that comes from the bond. And you can also do this in the final step here as well, is we get rid of the positive charge. Now, I've said this before when we went through, that it can either be as a 2-step process or as a 1-step process, that intermediate, and we end up with our product. Here, CH3. All I've done there is I've just rotated the molecule round by 360 degrees in order to view that. Your marks here, you're going to end up with about 5 marks for that question, 1 mark for each of your correctly drawn curly arrows plus your intermediates. Gives you around about 5 or 6 marks for a question like that. And the name of the mechanism is, of course, nucleophilic addition elimination that you pointed out. So a good one to do, because it's, other than free radical substitution, it's not one that we've seen so far this evening. Then step 2. Okay, so step 2. I was looking all the way up here to try and work out what happened. But of course here on step 2, they've added NO2 to the bottom of the molecule. So here, we're then looking at the reaction of the benzene system. And it's quite common for them to do this sort of thing where they give you a molecule and they'll look at 2 different bits of it to react. So you've just got to think about what is reacting, what's being formed. Here we've seen a reaction of the nitrogen. We know that the nitrogen is a nucleophile, so we talk about nucleophilic substitutions. Now we're looking at the benzene part, and we're now looking at an electrophilic substitution. And identify a suitable reagent or combination of reagents. Okay, so here we have to talk about forming the nitronium ion. Whilst you're working out how we form the nitronium ion, you can tell me the required reagents to make the nitronium ion. Absolutely. So concentrated H2SO4 plus concentrated HNO3, and we get the electrophilic addition. Well, we get the attack to the nitronium ion to start with. We form the intermediate, and then we have the hydrogen come in. You're also going to do this at less than 55 degrees Celsius. Fantastic. Okay, so let's keep moving. Identify a suitable reagent or combination of reagents for step 4. Draw the repeating unit of the polymer formed by reaction of 1,2,4-diamine. Okay, so step 4 then. Step 4 is the tin and concentrated HCl. And there we got the reduction reaction. I think we talked about that one already this evening. It's common to ask there for those reagents. You don't need any mechanism for that one, but you've got to know from the nitrate, the reduction of the nitronium ion, oh sorry, the nitrobenzene to form the phenylamine. And okay, draw the repeating. Okay, so when we're drawing the repeating unit, well, we got starting off with 1,4-diaminobenzene. So here's our 1,4-diaminobenzene. So, okay, so where do you put the positive charge on NO2? That goes on the nitrogen. Yes, you're correct, Anna. On the nitrogen. Okay, and then we got the pentane dioic acid. The key here is you've got 3 of these because you've got 2 carbons on either end of the molecule. And so the repeat unit ends up forming a condensation reaction. We lose OHs from either end and a hydrogen from either end, and we end up with a molecule that looks like that. Okay, question 9 and 10 then to finish up. We're about 26 minutes past. We're not doing too bad. Describe how you'd observe with each compound. What you'd observe, well, here, okay, this is a carboxylic acid and therefore it is acidic. To test for this, you add sodium carbonate. You observe fizzing with F and not with E. So you're simply checking whether or not it's an acid or not. G and H. Here we've got a ketone, and here we've got a propanoyl chloride. The best thing to do here is probably a test you could do if you is yes, did I not write that? They're not quite the same thing, but they both work, Anon. So sodium hydrogen carbonate and sodium carbonate will do the same thing. The important thing is they're both soluble carbonates. Here, if you add water to this one, you would form a product plus HCl, and you would check to see the acidity of the product, I would suggest. No worries. Sorry. I'm just checking for an ion here. Sorry, I've gone a bit quiet here just because sorry, I'm looking at the wrong bit. Go on, where are we up to? Yes, and on silver nitrate would work here. Well spotted. So if you added water and then AgNO3 would simply work. You get a white precipitate. Absolutely. A good choice. Fantastic. Part 3 then. The final one here. You're testing the difference between here a primary alcohol versus here a tertiary alcohol. So this one, if you use acidified K2CR2O7, the primary alcohol would go from orange to green, and this one we would see no change. Okay, part B. We'll have a look at this one next week because this one is really dealing with proton NMR. We'll do plenty of NMR next week. And this one. So we will look at this. In fact, we'll go, if it's good with everyone, we'll go with Monday for NMR spectroscopy. And we'll have a quick look here at question 10A. Okay, compound C can be synthesized from ethene in 3 steps as shown below. Name compound C and draw a structure for each compound A and B. State the reagents required for each step and name the type of reaction involved in conversion of B into C. So name compound C. I've got to be able to see compound C to start with. Okay, so that's based on butane. So it's going to be 1, 4, because that's the position of the amino groups. Di, because we have to say there's 2 of them. Amino butane is the name of C. Well done. Draw a structure for each compound A and B. I'm going to have to work this out. I think C4. Ethene in addition reaction. I've not actually looked at this question yet. So A must be an addition reaction in which to form some sort of bromo ethene. Okay, so here, yeah. I think I got it right. Okay, so draw a structure for each of compounds A and B. So compound A. Let's see what we've got. Yeah, not quite. Yes, anon 6598. You're right with 1,4-diaminobutane, but bromoethane is not going to quite work. What we've got to do here is we're starting off with, we're finishing with 4 carbons in the chain. We're starting off with 2. So somehow we've got to find a way to add 2 carbons to this chain. The way we add carbons, remember, is by reacting them with nitriles. So if we want to add nitriles to this chain, we're going to add, somehow we want to add Cn minus to it. If we want to add Cn minus, we've got to get to some sort of haloalkane. Now we've seen that, but we want to add 2, so really we want to add 2 Cn minuses. So in this case, when we're starting with ethene, rather than doing this with HBr, if we do this with Br2, what we're going to end up with is a bromine at one end, a bromine at the other end. And so our molecule here is actually going to be 1,2-dibromobutane. And then we can do the substitution reaction with this, with 2 times KCN in acid, and that will give us C triple bond on either side with a nucleophilic substitution reaction. And then again, the final step with that slightly funny one that we need to know about with the lithium aluminium hydride in dry ether, we would then go to form the diamino group. So that is quite a difficult question on synthetic pathways. But again, it's a case of realizing that you need to add carbons, and then before we need to use nitrile groups. So this is a reduction, and that's going to be lithium aluminium hydride and dry ether, or platinum nickel, whichever one, platinum nickel hydrogen gas. As we saw, 2 KCN, that's in ethanol and warm. That's a nucleophilic substitution. This is bromine. It's an electrophilic addition reaction. Okay, difficult question. I can see if any of you struggle with that. That is quite difficult. Okay. Draw the repeating unit of a polyamide form when C reacts with hexane dioic acid. Okay, so we've got hexane dioic acid here. We've not really looked at condensations. That's therefore going to form CH2 4NH. And why polyamides are degraded by sodium hydroxide, whereas polymers such as polyethene are not? Well, polyethene here has got strong carbon-carbon bonds, whereas polyamides have got a here, they've got a polar C double bond O group, which is susceptible to nucleophilic attack. Okay, so loads of chemistry there, dealing with lots of synthetic routes and pathways that we saw the other night, requiring all of the mechanisms that we saw from both the AS and the A2 course. There's lots more questions. I can always provide more. I will put the answers there up on the past webinar page. And I think indeed the past webinar page should be there already if you want to view it with tonight's content on it already uploaded. And as I said, I will add in the last yes, and on 3085. Don't worry, we will definitely have NMR on Monday, assuming that enough people want to do NMR. Don't forget, please do share the website with any colleagues. The more people, the better it can be. And also, I hope to have the chat up and working for you all next week, so that we don't have this sort of blue screen. NMR on Monday, and I look forward to seeing you then. Thanks all for watching. Take care. Don't forget to share, and I'll see you all soon.